Okay, let's unpack this. We've all been there, right? That little red battery icon popping up way, way too soon. That frantic hunt for a charger. It's basically a universal anxiety we carry in our
All
pockets.
right.
But what if I told you that that mundane little battery, well, it's actually at the heart of this really intense, high-stakes battle brewing in the smartphone world? Today, we're taking a deep dive into exactly that. We're calling it the silicon-carbon divide, smartphone battery battleground, where we've got this revealing report, our source material, and it lays out a pretty bold assertion. Basically that the upcoming Samsung Galaxy S26 will likely struggle to match, let alone surpass, the battery life of its Chinese rivals.
And that's a crucial point because let's face it, smartphones aren't just phones anymore. They're our primary connection to everything. They're indispensable tools, right? For communication, entertainment, work, everything. And this increasing reliance has dramatically amplified the demand for robust power sources. Seriously amplified. I mean, we're talking about a global smartphone battery market valued at over $30 billion in 2023, and it's projected to shoot past $50 billion by 2030. That puts immense pressure on manufacturers. For years, we've seen these incredible leaps in displays, cameras, processors, but batteries, they've kind of been the bottleneck. So yeah, it's safe to say battery tech has truly transitioned from being, a secondary thought to a primary battleground for market leadership.
Right. So if battery tech has gone from just a component to the absolute core of what defines a flagship phone, our mission for this deep dive seems pretty clear. We're going to pull back the curtain on this new tech, compare the very different strategies of the big players, Samsung, the leading Chinese manufacturers, and ultimately try to figure out what this all means for your next smartphone purchase and honestly how you use your phone every single day.
Okay, let's start with the buzzword itself then, silicon carbon or SiC batteries. What exactly are they and why are they generating so much excitement?
Okay, so the fundamental distinction from, traditional lithium-ion batteries, it lies in the anode material. Conventional lithium-ion batteries use graphite in the anode. That's standard. SiC batteries, on the other hand, they replace or sometimes just supplement that graphite with silicon. And here's the game changer. Silicon has a theoretically much higher capacity to hold lithium ions. We're talking maybe up to 10 times more than graphite by weight. Whoa, 10 times. Okay, so if silicon is the game changer, what are the tangible benefits for us, the users? What does this mean for someone who just wants their phone to, last longer?
Right. It delivers several key advantages, like directly to your pocket. First off, enhanced energy density. This just means more energy stored in the same physical space. So for you, that translates directly into, say, watching that full movie on a long flight without battery anxiety, or, getting through an entire day of heavy use without hunting for an outlet. It also allows for thinner, lighter phone designs, even with these bigger batteries.
Thinner and lighter with bigger batteries. Okay, that's interesting. What else?
Second, faster charging capabilities. The improved conductivity and ion exchange, they allow for significantly quicker charging speeds. We're now seeing many SiC-equipped devices supporting over 100W wired charging, which can cut full charge times down to under 40 minutes sometimes.
Under 40 minutes for a full charge. Wow.
Exactly. Third, extended battery lifespan. By managing silicon's swelling and shrinking during cycles better, these batteries show reduced degradation over time. That could mean a longer overall operational lifespan for your phone's battery. Some manufacturers are even claiming up to 4 years of durability.
4 years.
Yeah.
That sounds almost too good to be true for a smartphone battery these days.
It's a bold claim, yeah. And finally, lower heat generation. They have enhanced thermal efficiency, which means less heat, especially when you're pushing the phone hard, like with intense gaming or long video recording.
Okay, 4 years durability, less heat, faster charging, more power. It sounds amazing. Are these claims really holding up in the real world, though, or is there always a catch? What are the actual hurdles engineers face trying to implement this tech?
That's a really good question. And yeah, it speaks to the core challenges. The potential is huge, absolutely. But the primary hurdle is structural integrity. Like I mentioned, silicon undergoes substantial expansion and contraction during charge-discharge cycles. It literally swells and shrinks. If you don't manage that properly, this volumetric fluctuation can, compromise the battery's integrity. It leads to degradation over time. Think of it like a sponge constantly being squeezed and released eventually. It might just break down.
Right, that makes sense, like physical stress.
Exactly. The second big challenge is manufacturing complexities and costs. Integrating silicon into anodes, it adds considerable complexity to the production process, and that, can drive up costs significantly.
So how are engineers trying to get around these issues? Because clearly some companies are making it work.
They're employing several clever strategies, yeah. One is combining silicon with carbon materials. The carbon provides mechanical stability, kind of like a supportive structure, and it also improves electrical conductivity. They're also constantly researching alternative materials to further limit that expansion. And beyond just the physical chemistry, there's a huge push into developing advanced AI-powered battery management software.
Ah, the software side.
Right. These intelligent systems can dynamically control battery usage, like per application, and monitor charging patterns in real time. The goal is to reduce stress on the battery cell itself and enhance its longevity that way. And, this raises a really important strategic question for manufacturers. They have to balance those immediate eye-popping performance gains like massive mAh figures and super rapid charging against sustained product reliability and customer satisfaction over many years. It's a critical choice.
A real balancing act. So who's making the bolder choice in this battery battle, Ben? Who's aggressively embracing this SiC technology? And what kind of real-world results are they actually seeing?
Well, it's become pretty clear that Chinese smartphone manufacturers have emerged as the frontrunners here. Brands like Honor, Oppo, Xiaomi, Vivo, OnePlus, Redmi, IQO, Realme, they're actively incorporating SiC into their flagships, and sometimes even mid-range devices. They definitely see superior battery life and charging speeds as crucial competitive differentiators. And let's face it, a very crowded market.
So give us some specific examples. We've heard some pretty jaw-dropping capacity numbers thrown around.
Oh, yeah. We're seeing a consistent push well beyond the 6,000 mAh mark now. Some phones are even hitting 6,500 mAh. For instance, the Honor Magic 7 Pro already boasts 5,850 mAh using their third-gen SiC tech. And Honor was actually the first to bring that tech outside China. The OnePlus 13 is packing a 6,000 mAh dual-cell SiC battery. Looking further, the Redmi K80, and that's not even the Pro model, has an impressive 6,550 mAh.
A 6,550, wow.
Right. And Xiaomi's upcoming 15 Pro is rumored to integrate a 6,100 mAh SiC battery with this ultra-high energy density. They're apparently increasing capacity significantly while actually making the phone lighter. So these aren't just minor bumps. It's a fundamental rethink of what's possible in battery capacity without making the phone feel like a brick. And looking ahead, some predictions suggest China-centric smartphones could even hit 7,000, maybe 8,000 mAh in 2026.
Crazy numbers.
Yeah.
So, okay, it's not just about capacity, though. It's also about how quickly you can fill that capacity up, right? What about the charging speeds?
Absolutely. That's a huge part of the user experience, a massive part. And we're seeing a clear trend of 100W plus wired charging speeds basically becoming standard on these flagships. The Honor Magic 7 Pro and OnePlus 13 support 100W. The IQO 13 and Redmi K80 Pro jump up to 120W. The Realme GT7 Pro, for example, they claim it can get a 50% charge in just 14 minutes with its 120W charging.
14 minutes for half a charge. I mean, who hasn't been in that panic, right? Trying to squeeze a few more percent out before rushing out the door.
Exactly. This kind of charging speed is a genuine game changer for just daily convenience, no question. And many of these flagships also support high-speed wireless charging too, typically ranging from 50W up to maybe 80W. What's particularly fascinating here, too, is the discussion around the actual silicon content. Initial adoption was maybe around 10% silicon in the anode, but now these Chinese manufacturers are planning to increase it by like 25–30% next year. Next-gen phones might ship with 20% silicon content. They are really leveraging SiC to keep those compact phone shapes while offering significantly longer endurance. They're leading this capacity race, absolutely, and they're adopting this kind of holistic, full ecosystem approach for battery performance.
Okay, so on one side of this battery battle, we have these Chinese manufacturers deploying bigger, faster batteries using SiC. It really feels like they're making aggressive moves. How does Samsung, a traditional powerhouse, respond to that kind of offensive? What's the battery outlook looking like for its upcoming Galaxy S26 Ultra?
Well, reports and leaks, they strongly indicate the Galaxy S26 Ultra will likely retain a 5,000 mAh battery. This has been a pretty consistent capacity across all the Galaxy S Ultra flagships going back to the S20 Ultra. So it really signals a continuation of Samsung's, let's say, conservative trend in this specific area.
5,000 again. So why? Why isn't Samsung jumping on the SiC bandwagon like its competitors? It honestly feels like they're falling behind, at least in the raw numbers.
Yeah, it looks that way on paper. Samsung's reluctance, though, it seems rooted in a very deliberate, very cautious strategy, one that fundamentally prioritizes safety and long-term durability above almost everything else. And look, this is a direct consequence of past battery-related incidents. We have to mention the Galaxy Note 7 debacle.
The Note 7. Still casting a shadow.
Absolutely. That incident isn't just a footnote in Samsung's history. It's still actively shaping their strategic decisions today. It creates a heavy burden for their engineers, you could say. The primary technical concern for Samsung is exactly what we just discussed, those long-term durability issues due to volume expansion of the silicon carbon anode. Samsung has this deep-seated commitment, almost a policy, to not release new battery technologies until they are absolutely fully satisfied with extensive long-term testing, and that process can take years. Now, this approach, while you can understand it for safeguarding their brand reputation, it definitely leads to an innovation lag in raw battery capacity and charging speeds. And that risks alienating those performance-oriented users who are looking for those big headline numbers.
Okay, so if they're consciously not going SiC, at least for now,
Mm-hmm.
what alternative battery advancements is Samsung pursuing? They must be doing something to keep up, or at least try to, right?
Yeah. Oh, definitely. They're focusing on incremental advancements within their existing proven lithium-ion chemistry, really optimizing what they already have. For instance, they've partnered with a company called ITM Semiconductor for advanced protection circuits. They use something called epoxy molding compound, or EMC technology. This tech apparently improves heat dissipation, shields the battery components from moisture, prevents electromagnetic interference, and interestingly, by making the protection circuit itself smaller, it frees up a tiny bit of internal space. Now, unverified rumors suggest this could potentially enable a slightly larger battery cell, maybe 5,500 milliamp for the S26 Ultra. That would be a 10% increase, which isn't nothing.
A modest bump, maybe.
Yeah.
What else?
They also reportedly plan to switch the battery's housing material to stainless steel. They call it SUS CAN. Think of it as a tougher yet potentially thinner protective shell for the battery components. Again, that reduction in casing thickness, even if it sounds tiny, frees up valuable internal volume that allows for more actual battery cell material, leading to potentially higher energy density within the same overall phone size. And of course, they leverage advanced software optimizations and AI-driven battery management. Those algorithms have reportedly improved efficiency by maybe 10–15% in recent years, squeezing more life out of the same R. So yeah, it's a clear divergence in R&D philosophies. Samsung prioritizing risk mitigation and steady incremental improvements versus competitors making these bolder, potentially disruptive technological leaps with SiC.
Okay, let's get to the brass tacks then. Let's really compare. How does the rumored Samsung Galaxy S26 Ultra actually stack up against these leading SiC flagships in terms of real-world battery performance?
Well, the difference in raw battery capacity is pretty stark, as we've said. Samsung's expected 5,000 milliamp, or even that rumored 5,500 milliamp. It's significantly lower than the 6,000 milliamp plus capacities that are becoming common in Chinese flagships. I mean, some models like the Redmi K80 are already hitting 6,550 milliamp, and future projections are even higher. And when we look at empirical test results, some early comparisons, the disparity becomes even clearer. Take the Vivo X200 Ultra, for example, with its 6,000 milliamp SiC-battery. In some tests, it achieved around 9 hours and 37 minutes of screen-on time. It particularly excelled in YouTube video streaming tests, lasting like 13 hours and 41 minutes. That's nearly 50% longer than the Galaxy S25 Ultra in the same test. It also showed strong 3D gaming performance.
Wow, almost 14 hours of YouTube. That's impressive. And the S25 Ultra.
In contrast, the Samsung Galaxy S25 Ultra, with its 5,000 milliamp traditional lithium-ion battery, recorded around 8 hours of screen time in similar tests, and YouTube streaming was under 9 hours, so quite a difference there. While its 3D gaming was strong, sure, it clearly lagged in video streaming endurance and overall screen time. Now, it is worth noting that sometimes even the Apple iPhone 16 Pro Max, with a technically smaller battery, around 4,685 milliamp, it often outperforms the S25 Ultra in overall battery life tests, especially things like web browsing. That just shows how crucial software optimization is.
Right. Optimization plays a big part, too.
It does. But the SiC technology still seems to offer a distinct advantage in many demanding scenarios, especially for raw endurance.
And the charging speeds, we touched on it, but that's another area where the difference feels pretty significant and directly impacts daily life, doesn't it?
It absolutely does. I mean, Samsung's typical 45W fast charging, it just pales in comparison to the 100W, even 120W speeds routinely offered by the Chinese flagships now. This directly impacts your convenience. Plugging in for 15 minutes yields vastly different results, and it creates this clear perception gap in the market. People see those charging speed numbers. So yeah, that core difference really stems from this fundamental technological divergence. Samsung sticking with optimized traditional lithium-ion versus the Chinese OEM's aggressive embrace of the more energy-dense silicon-carbon chemistry. They are just taking very different paths right now.
Okay, so this Kainsi tech is shaking things up now.
Right.
But is it the final word in battery innovation? Or is this just, one chapter in an ongoing story? It really feels like a continuous innovation race.
Oh, it absolutely is. It's definitely a continuous innovation race. And SiC is just the current battleground, you could say. There are several other really promising emerging battery technologies bubbling up on the horizon. First, maybe the most talked about, are solid-state batteries. These replace the liquid electrolytes found in current batteries with a solid material. The potential benefits are huge. Higher energy density, significantly longer lifespan. Some research suggests up to 7 times more recharge cycles and improved safety because they're inherently less flammable, maybe even fireproof.
Solid state sounds like the holy grail almost.
It kind of does, but they still face major challenges in scaling up manufacturing and getting costs down, but the potential is enormous. Then there are lithium-sulfur batteries. These are theoretically capable of storing up to 8 times more energy per unit of weight compared to standard lithium-ion. Plus, they utilize sulfur, which is more abundant and sustainable than some materials used now. The challenges there include things like corrosion and ensuring long-term durability. Commercial availability for some applications is maybe targeted for around 2028.
8 times the energy. Okay, that's another big leap potentially.
Exactly. And then way out on the cutting edge, you have things like quantum batteries. These are still largely proof of concept devices, harnessing weird quantum states for potentially extraordinary charging speeds, like near instantaneous charging. Very futuristic stuff. And there's also research into paper-based batteries, quasi-solid state, cobalt-free lithium-ion, sodium-ion, which uses cheaper sodium, iron air, zinc-based batteries, loads of different chemistries being explored. So yeah, while SiC is the fight right now, the future holds even more revolutionary possibilities for how we power our devices.
Okay, so if we connect all this back to the bigger picture, especially for Samsung, what are the strategic imperatives for them to navigate this really dynamic battery landscape? They can't just ignore SiC forever, can they? Or just hope optimization is enough?
They absolutely cannot afford to ignore it, no. Several imperatives really stand out for Samsung strategically. First, they probably need to reevaluate their SiC adoption timeline. That means maybe accelerating their internal R&D and testing protocols to mitigate those durability concerns faster. The market is just moving incredibly quickly. Second, if they do decide to maintain a cautious approach for longer, they absolutely must communicate safety and reliability effectively. They need to proactively emphasize superior long-term durability, consistent performance over years, and enhanced safety features as key differentiators. Make it a selling point, not just a lag. Third, and this is critical for the long term, they need to seriously invest in next-generation technologies beyond standard lithium-ion. This means significantly increasing investment in those transformative technologies we just talked about, like solid-state and lithium-sulfur, to ensure they don't get left behind in the next race. And finally, they should absolutely continue to leverage their ecosystem strengths for power optimization. Keep optimizing power consumption across all their hardware and software, the processors, the displays, the AI battery management. They can draw lessons from devices like the iPhone, which achieve impressive battery life through tight system-level integration, even with smaller raw battery capacity sometimes.
Right, play to their strengths in optimization while maybe accelerating the next big thing. So, okay, to summarize this whole deep dive then, the core tension seems crystal clear. Samsung's safety-first, very cautious approach to battery innovation is putting it at a significant disadvantage, at least right now, against Chinese OEMs. These companies are aggressively embracing silicon-carbon technology, which is fueling this full-blown capacity race and delivering significantly faster charging speeds that Samsung just isn't matching at the moment.
That's right. Based on current trajectories and leaks, the Samsung Galaxy S26 is likely going to struggle to surpass, maybe even match, many top Chinese phones in raw battery life and charging speed benchmarks. And that creates a significant competitive gap in a market where, let's be honest, extended battery life and rapid charging are increasingly key purchasing criteria for you, the consumer. It matters a lot to people.
It really does. Which leaves you, the listener, with a final provocative thought, I suppose. What will truly define battery leadership in the future? Is it simply going to be about the raw capacity numbers and the charging speed race? Or is it more about that subtle, complex dance of balancing cutting-edge performance with unwavering safety and that crucial long-term reliability? Something to think about. What do you prioritize most in your next smartphone?